Hello and welcome to YMT114 Principles of Software Engineering. This is chapter 5. So we will be discussing the topics related to system modeling, and we will just address the first part of it. We will speak about a number of models within this chapter, but in the first part we will speak about particularly two models in particular or specifically. So we will just go through the topics covered: system modeling, system perspectives, UML diagrams, unified modeling, that means language diagrams, context models, system boundaries, interaction models. So within interaction models, we will speak about two specific design or UML diagrams that we have for modeling. Let's just go and check the slides. Let's go ahead and check the slides one by one and see what we have as contents. The modeling of any software system is exactly the process of achieving or producing an abstract view of the system itself. Abstract here means what? We set aside all the details of the system and we provide a model or an illustration or a design of a drawn components of the system where we have certain perspective to be addressed. You may not be aware of perspectives now. However, imagine we have a software, and the software you would like to address one of its aspects or perspectives, whether it is context, where it fits into the application or into the operating system, how it fits with other applications surrounding it. So that's a context view. Or we may think about another perspective of activity, how the software itself is processing inputs and producing outputs, and etc. So we model these usually in individual cases to address some perspective in a modeling view, an abstract view to have an illustration, visual illustration of how the system itself is fitting together and how it interacts, and how, if there is any consequence or sequence of events, it happens. So this is exactly the idea of modeling. Now, currently, the most common or the most commonly used software or application for modeling software applications or software projects is the UML, the Unified Modeling Language. It's actually the most widely used tool for modeling software. It has a number of models and diagrams and a variety of you can say models within it. So that's why it's widely used, and I was hoping that we could catch it at an earlier time, but no problem. At the end of this chapter we will have an extensive discussion about UML and how we can design with it. Why? Because it will help us even in producing codes, and that's interesting. Later on it will facilitate the job of complicated software projects by shortening the time of producing some codes where we can review them. For sure, we cannot have these codes directly for the implementation. However, they make our job easier in producing the overall implementation of any system. So the idea of system modeling helps actually analysts to understand the functionality of the system, and also you can say it's an aid, or it's a sort of an intermediate that helps the clients to explain things to customers or to make the proper communication in a visualized way. That means with some graphical representation where people, human beings, can perceive things in a much better way. So look at the system modeling, the uses. The first one is actually during the requirements engineering process, and we explained about requirements engineering process, what it is in brief, that we need to get in this process what the users are requiring from the system and what the system is actually supposed to produce. So system and user requirements. We explain about the process itself in details. So within this or during this process or in requirements engineering process, we need to model the system for what? For as an aid or as actually a tool to assist in discovering or producing the proper requirements. So you can properly communicate with the users or the stakeholders of the software and show them a representation of how the system will be used and how it will produce the outcomes which is supposed to produce. Then we also use the modeling during the design process. Why? There are separate, you can say, groups during the software development phases or throughout the software development phases. Some of them are designers. These designers create a model for the system, and this model is provided to the implementation team, those who write codes. So they give a description about the system, but this description is graphical. It's like a model where they implement it. So the team will implement based on a ready model designed by the design team. After the implementation, we use the system model for documentation. Why? We document whatever the model we produce, whatever the software we produce, we document its model. Why? We may use it later on. We may use it also for maybe for bidding for another project, maybe for maintenance. So many reasons we need to keep a copy or a documentation copy of whatever project, software project models that we created. What kind of models do we create while developing a software? We have two main types of models that we usually have. The modeling of the existing systems. So usually we do this specifically for requirements engineering, either to explain or to clarify or to show in a more illustrative way how existing systems are doing things. And based on it, we can use this scenario, or we can use how these the way by explaining. Sorry, we can use the way system produce things to explain or elaborate to stakeholders maybe certain points about the systems and what we should avoid and what we should focus on. So we can use modeling of existing systems for this purpose, and modeling of new systems actually as a base of discussion. As I said earlier, that we usually use some graphical visualization to make a proper discussion or a proper communication with the stakeholders to clearly understand the requirements. Also, for new systems, for the implementation phase, we need modeling. Also, for the documentation, we need modeling. So these are the main uses. For something we have not yet discussed, we call it model-driven engineering process. We will discuss it at the end of this chapter. For this kind of process, or actually a special type of process in software engineering, we can generate a complete system or create a complete system implementation just from using a model. And we will see this one practically by some examples later on. Usually we don't do this for big projects. It's not usually a valid way, or not, let me not say a valid, an efficient way for producing such complicated systems, but sometimes for small to medium scale software systems, we can do that using model-driven processes where we produce some ready codes from modeling, and then we just modify quickly these codes and have a look over all whatever the automated codes are produced, and then just have the user's opinion, and then get a new or a final version of the system based on automated code generation. So we will discuss this one later on, not now. System perspectives. I said at the beginning we have different perspectives of the system to be modeled. external perspective. Now leave the system alone. We have a system. Now the system, any software system, must fit in an environment. Any software system is not isolated. It needs other software packages or applications to fit with, starting from operating systems and go to other applications that they require in their own process. You may ask, or you may think, why is that? Why do not we have a totally independent software that runs on its own? It would be extremely complicated. Why? You would have to address operating system to run the software on a machine. You would have to have whatever dependency that any software requires on other software packages. You will have to implement it in that software to run the software on its own. So whatever application you need to have, or whatever functionality you need to have from that software, you need to implement it from the software itself. You cannot borrow it from other available software or have it as a dependency on other software. So in that case, we have external perspective, whatever outside of our system, however our system is actually fitting in it, or it's coming within the context of our system, its environment. So this is a view or a perspective. We have the interaction perspective. It's exactly modeling what? The interactions between the system and its environment. That means maybe inputs to the system and outputs from the system, okay? And also the interactions between the components of the system themselves. So within the system, inside the system, we model the interactions. Structural perspective, where we model actually the organization of the system. And you guys, I'm sure you studied things about data structures by now. If not, you will study soon. The idea is every software has its own design of data structure, its own organization of data structures, the view of the software system in terms of its own organization and how the data is processed in the system. So this is another perspective. Also behavioral perspective. This perspective is actually concerned with the dynamic behavior. So while the system is actually responding to events, if there is an event, and event is actually something like triggering the system to do something. So it's just a trigger. Once we initiate this trigger, so it's an event, what happens to the system? So what kind of response do we have? This is exactly what we call dynamic behavior of the system, or the behavioral perspective of the system. UML diagrams, up until now you have already seen UML and you studied it in Algorithm and Programming 1 and 2. But the idea of UML diagram diagram or diagrams or types actually is much more complicated than what we have seen in Algorithm and Programming. We address just the class diagrams, just one of them. We have many others, not just restricted to the ones that you see here: activity diagrams, use case, sequence, class, state diagrams. No, there are others. However, these are the main ones that we usually have commonly while developing a software projects. You may have other subsidiary processes and diagrams in UML that you may need to have while modeling a project. So what's the activity diagram? In brief, this kind of diagrams represent or show the activities involved in a process. So imagine we have a process of anything. You can think of any process that your software is doing or is achieving. So what kind of activity is available in that process? The modeling that activity or the series of activities while processing that sort of data is called activity diagrams, or actually is done based on activity diagrams. Use case and use case diagrams, actually we try to model or we try to show the interactions between the system and its environment. So we focus on the system and the outside of the system, some actors from outside of the system and actors from inside the system. So this is what we will study in a while after a few slides. Sequence diagrams, actually sequence diagrams, the elaboration of use case diagrams. We take one particular use case and we show the interactions in details inside the components of the system. For the use case, we just show the interaction from outside with one particular, you can say, component of the system. However, if we want to elaborate it, if we want to have more detailed explanation about it and visualization of it, we go for a sequence diagram where we show the series of interactions inside the system components along with the actors from outside of the system. Class diagrams, you guys are familiar with class diagrams, why we studied it before. However, they are mainly related to the object classes. That means the representation of the objects that we have and the associations between the objects or classes, if you like. State diagram, where we actually show the reaction to internal and external events, and just try to make a link state diagrams and have a look at the behavioral. So we have events. So these are usually linked or connected to such scenarios. The use of graphical models, as I said earlier, the graphical models actually create an easy way for discussing the system requirements. So the idea of having system modeling in a graphical way creates an easy environment or a convenient environment for discussion. Now, if we model existing systems, some existing systems, we don't have to have an accurate modeling for these systems. It doesn't have to be fully accurate, nor does it have to be complete. We can close an eye on having a complete and accurate modeling of existing systems. Why? Because we are modeling these existing systems for the purpose of viewing how they work and what kind of weaknesses they have. We are not modeling them to build them. It's not, our aim is not actually building them. However, if you are looking for building some existing system, although it's not logical, it's not a logical idea to do so, then you have to have an accurate and complete modeling. Also, if we are going to model a system for documentation purpose, then it shouldn't be complete. Why? Because we model things that we are interested in documenting. So, while you're interested in subsystems, not the whole system as 100% of modeling activities, you're interested in maybe 70% or 80% of the most important. The other parts are just commonly known to people. We don't have to document them in a model. However, the 80% or 70% or 50% or whatever the percentage of the modeling that you need to have in that documentation should be accurate. So when you are documenting for a newly developed system, you have to have an accurate representation of the models that you have. If we are going to create a model for description so that we pass it to the implementation team, and based on it they create the implementation, the coding part of the software, the idea of the models here, or the main concept of modeling here, is that we have to have both accurate and complete modeling scenario. Why? We shouldn't, and actually not we cannot, we shouldn't, we must not implement based on incomplete or inaccurate representation or model representation of a system. Why? Because we will end up having some, you can say, speculations about what we are not quite sure, plus we will have erroneous implementation due to the incorrect visualization of the software itself, because we are going to build based on what we have as a design. So any mistake in that model will reflect on the implementation. Any actually lack of the design will also reflect on the implementation. Context models. We spoke about the context actually, and as I said, what we do is we look at the environment of the system. So what's surrounding the system? And this is what we refer to in a technical term by a technical term, the boundaries of the system. So boundaries determine what's inside and what's outside of the system. And why do we need to discuss boundaries of the system? Boundaries have actually a lot of influence on the system implementation and design. Why? To decide what's inside the system and what's not inside or what's outside the system, and to make decisions about the boundaries of the system, we may have a lot of, you can say, political influence from stakeholders. Why? Imagine that the stakeholders or the client who's asking for the software is requesting some certain pressure on some part of the company, not the other, or some certain, you can say, approval of a manager before doing certain task. So this is a political influence, and it affects the boundaries of the system, what lies within the system and what's actually outside of the system. Now, this is what I said what I said a minute ago, the boundaries of the system, what's inside and what's outside. And also, not only this, the dependencies that we have in our system while we are developing it. Our system is dependent on what? So what kind of environment or other software applications that our system should depend on. Okay, you may ask, or you may say, what's the point? Why do we need to have a view about the boundaries, or why do we need to discuss them? Well, they affect actually the system requirements. So the understanding of system requirements is mainly affected by the view of the boundary. And as I said, usually boundary, or the determination of the boundary itself, has a lot of things to do with the political judgment, or actually the decision of stakeholders. And due to that, we need to have a clear definition of the boundaries of the system so that we know how to build the system and what's inside of it and what's outside of it. What kind of dependencies do we have on other software systems or the environment that's surrounding our system. Now look at the context of the managed care system. By now you are extremely familiar with the managed care. We give it as a typical example of a software system for healthcare of mentally sick people. So basically we are discussing a system at the core, the center here, and we have other systems that are considered the environment. So these are outside of our main core of the system, and we have dependencies on our system with those. Now you may say, why do not you include all of them along with the system, and that's just one system? If we do that, what will happen? First of all, our system will become complex. So having said that the system will be complex, that means it will be slow. Its performance will be not very efficient, and it will need big memory size to be installed. So you don't need to have that. That will actually lower the specifications of your system, and that will create some sort of a weak system when it comes to the requirements of non-functional requirements, like things related to the size of the software and the reliability or whatever of the software, the performance. One more thing. Now, having included many subsystems all together in one system may create also vulnerabilities in the system. Why? Because if we create our subsystems and secure our main core system so that we try to avoid vulnerabilities from subsystems that allow the access to our system, that will be actually securing our system, or the core part of our system. That's why we build some other systems surrounding our system, so that we leverage our system in least, you can say, cost in terms of performance and in terms of size or similar things. One more thing I have to say about these systems: some of them are already ready. We don't have to develop them from scratch. So that will be inefficient to do so. It will need time and effort, and actually some of them are already available. Why do we need to design them from zero? Why do we need to implement them from zero? So our core system will be implemented from zero, and then we can surround it by other systems to create the whole view of our own system. Our process perspective. So we spoke earlier about the context and the modeling of the context. So now imagine if we have a process, if we would like to model this process, uh, how can we visualize this kind of activity? So we said about the context. Well, we said, as I said, we look at the system surrounding our system, or the environment, okay? How our system is fitting its own environment. But let's say we want to model a process which is happening in our system. So in that case, we need to have some sort of diagram to cover this kind of process. And it is widely available in software systems or software applications where we model the process itself so that we understand the mechanism and maybe the interactions or the movement between subsystems and the dependencies in the process achieving way. So in that case, we may have a model for the process itself and how it is achieved. You may think of activity diagrams to do such a scenario, and have a look here. We can think of modeling a process of involuntary detention. Let's say we have a risky person who is supposed to be detained for some mental health problems. And due to that, we can have this process model. The beginning of the process is actually represented by this filled circle. And then we have each and every process or sub-process actually, or activity surrounded by these, you can say, squares with the round edges or oval shapes. Actually, they are not perfectly oval. They are more about like rectangles with the soft edges. So confirm detention decision. While confirming this detention decision, we may have two processes at the same time, and they should be achieved in parallel in this case. They can be. So we inform the patient of rights, and then we have a record of the detention decision, and then we provide this specifically from the system. Then we may have like these two processes at once. Once they are done, we may check if the patient is dangerous or not. So we have a conditional statement here telling us if the patient is dangerous or not. In this case, well, if dangerous, we find a secure location to or place to detain the patient in or at. Or maybe if not dangerous, we can admit to a hospital, and we have to provide the admission. We have to provide this specification or this particular task using the system admission. Once those are done, and we need to achieve all of them as this kind of like a collector shows, then what we can do, we move to the next stage. We inform the social care, we inform the next of kin, we update the register, and this is done by the system of manned care, similar to the initial one. Once they are done, we have these two circles, a filled circle surrounded by another circle, which shows the end of the process. So this is the way we model processes in software, and it depends on your process. It depends specifically on what the type of the process that you are addressing while designing or while implementing your software, and then how the software is running things. So if you have a certain input or trigger or initiative of a process, what happens, the series of the steps taken in processing in order for the process to achieve or to do the final, or to reach the final destination or to achieve the final task. Interaction models, we spoke about the interaction models, where we said we have these interaction models that actually specify interaction from the outside of the system and the system itself, and between the components of the system themselves. So we may have an actor that interacts with the system, so an external, you can say, component or a system that interacts with the system, or the components of the system themselves that interact together. So basically, we use this kind of modeling of interaction during the requirements to help or to assist users or stakeholders in stating their requirements, so we can show in a graphical way about the interaction of the system and see if they clearly state their requirements or not. And if we are modeling the system-to-system interaction, not the external component or actor, we can check the communication problems. So if we are checking or if we are modeling the system-to-system interaction, then we are addressing communication and how it is done between the components of the system. So in brief, what we are looking for here is either the interaction between an external component or an external actor with a system, or the components of the system themselves, and both of them actually help us to check things similar to either clarifying requirements or checking for the communication problems. Sometimes we may need to see if we are speaking about component level, so component to component interaction, we may need to see how our system is actually producing the task that's supposed to produce. So the current structure of our system, will it produce the task, the required task or not? How is it producing it? Is it efficiently producing it? Does it need any software or any is there any dependency while achieving this kind of task? So we need to discuss these, all of them, while speaking about interaction models. We usually use case diagrams and sequence diagrams to model interactions, because use case diagrams usually model the external interaction with the system, while sequence diagrams are actually the elaboration of the use case scenarios. Why? Because they elaborate the details of the communication, while a use case, just one particular use case is achieved or is discussed. We will see how these are actually working. Use cases are actually a main part of the UML, and they help, or actually initially they were designed for requirements elicitation process. So while discovering the requirements, the use cases were used, but now they are a part of UML, so we can use them from different software packages like Star UML or Argo UML. These are free software packages. You can install them in your own computer and you can design or create or model the use cases that you like, and then you can transfer them to any other representation. So as I said earlier, when we discuss about use cases, we consider each interaction actually, or each discrete task, as an interaction or as a use case. So we have a task of registering something or unregistering something, or we have a task of viewing something, or we have a task of loading something or ordering something. All these are discrete tasks and we can represent them by use cases, and we will see how. So we have actors. Actors can be human beings like a user, or they can be subsystems or other systems, okay? Subsystems from our software system or other systems that our system is dependent on or it has an interaction with. So those are represented diagrammatically, that means visually by diagrams, and usually the representation by diagrams is not enough. So we use either a text to elaborate and explain the scenario of these use cases, or sometimes we use tabulated forms to explain how the use case is actually explained, or how to elaborate or to show how the use case is done or how it is achieved. Now look at this. This is a use case for transferring data from a medical receptionist to a patient record system. Now, do not be deceived by this stick figure. It's like a human being. It's not a human being. This is a human being. So medical receptionist is a human being. But for the patient record system is another system or subsystem from our system that allows us to record the patient information or update patient information or add things to the summary of the diagnosis of the patient. So it's an actor. Well, now you may think of it by what kind of action it's doing. It's actually allowing us to register things to the system, and that's why we call it an actor. So what's the action? The action is exactly transferring data, and it is represented by this ellipse or oval shape. And we usually have this arrow to show the movement initiated from where. Although sometimes we may request data from patient record system and it will be sent back to us, we don't show the arrow coming from here to the medical receptionist. Why? Because it's initiated from the receptionist. That's why we refer to it by this direction. Well, this is as simple as it is. Just an actor with this stick figure as symbolizing a human being. It doesn't mean that it is always a human being, as you see here. It's not, but it's just symbolizing an actor and then an action and the movement of the data transfer or the action, the movement of the procedure that we have. Okay, this is not clear enough. Well, I may understand it, but I may not have the full visualization of this scenario. Now look at the tabulated idea or the tabulated representation of, or the description of the use case. We specify the actors, what they are, the medical receptionist and the patient record system, PRS. So then the description here, we speak about the details of what is actually of the action that is being taken. So what's going on exactly now of scenario is the action taken by the one of the actors. Okay, so let's just go through it. A receptionist may transfer data from a Medicare system to a general patient record database that's maintained by health authority. So this is not exactly from our system. It's a sub-other system that is our system is dependent on, like maintained by the health authority of a certain nation. Similar to most of the countries that we may even visit, there is a general healthcare system maintained by the central government, or maybe the federal government, or maybe even the state government. So it depends. If you are using some certain health insurance, it will show on that health system. So basically, this one will transfer this data from a local system to maybe national system of healthcare. So in this case, we may update or transfer like information about address, phone number, etc. Summary of whatever the diagnosis of the treatment the patient has taken, or the patient has taken through maybe a week or a day or maybe a month. It depends on the policy of the clinic. So what kind of data are we sending? Patient personal information, treatment summary. What kind of stimulus do we have? User command. So it is stimulated by the user command. So this is the actor initiated the whole event. That's why we have this arrow pointing to this direction. Okay. Then what kind of response do we have? The confirmation that the PRS has been updated. So let's say I try to update, or there is a medical receptionist is trying to update the personal, the patient record information, or the record of a patient. How does he know, or how can he know that the information has been updated? So there must be an acknowledgement back again as an information to the medical receptionist that this thing is done, either a message telling that the information has been successfully updated, or the transaction has been successfully done, so on. So as we see it in most of our daily activities while dealing with software, like a payment order, for example, I'm sure that you are familiar with such a scenario where you place an order and go through a series of processes. Then after the payment is done and everything is cleared out, you get a notice that the whole procedure has been successfully done. So this is exactly the idea, confirmation. Comments. Now here we need to see what kind of specifications do we need to have. Well, the first thing is we need to have a security permission. Not anyone can enter the system and update or manipulate patient information, and that's why there must be certain security procedure for those who are dealing with this mental health care in order for them to be able to access to the system and manipulate or update or change the data based on what the requirements dictate. So now look, we may have interaction with a whole bunch of tasks here or actions. So medical receptionist, any receptionist may do register a patient or may unregister a patient, view patient info, transfer data, contact patient, and so on. I'm sorry. So there are a number of actions that may be taken by a medical receptionist, and for this purpose, or for this case, we can have different use cases separately, or we may combine all of them. However, if the system is complicated, we cannot combine all the use cases for each and every actor. We may have individual cases like this and then address them in sequence diagrams to see their details. Okay. So as I said, use cases are extremely abstract. Why abstract? Without this table, we will not be able to understand how things are done. Even with this table, well, you say data transfer or update. How is it done? How do you do it? From component to component within the system, how do you do this procedure? So if I need to know the details of this kind of interaction, what should I do? What's the elaboration, or how can we elaborate the process itself of registering or updating? So that's why we use sequence diagram. Actually, it's a part of UML as well. It shows the interaction between the components, the actor, and the system while processing the activity from the actor or the action taken by the actor until it reaches its destination. The interactions between the components, one by one, it shows it in details. So we go through the details of interactions from one point to another, from one component to another, and we see how objects are involved, how subsystems are involved, and so on. So basically it's like interactions based on object level. So components here we refer to objects. These are the smallest in software system usually, not all the time, but when we speak about such a thing, we speak about objects, and they are the smallest. How do we represent them? Let me go to the graphical representation and explain to you. In sequence diagram, we represent the actors along with the objects at the top here. Actors are created or represented by stick figures like this, and for the objects, they are represented by square with their names and the object instantiated from them. So we have objects instantiated from these we have an instance instantiated from these objects, okay? These are objects and these are instances of these objects. All right, so then we see the functions that actually derive the action. So view info and what kind of argument we need to send, maybe the personal or the patient identification. So based on it, we can get the information, and we need to provide the identification of the patient and also the user identification, because we need to have proper authorization. As you see, we need to have this proper authorization in order for us, once we get authorized, then we can view the patient information. Usually in sequence diagram, we have an alternative inside this box. So we have the normal process here, and we have these annotated arrows where we have the description on top of them, as you see, the functionality of the action taken, or whatever the method that initiates the action, okay? And those represent the lifetime of our objects or instances of our objects actually, not one object, okay? The idea here, we may have this alternative. So alternative to the whole process, we may have this one, like if the authorization is okay, we can view the patient info. If the authorization fails, then we will get an error message. So this is the alternative process, and usually we provide it so that if this one is not quite clear, or if it is extremely detailed, we can just go for this one, and it will just show, you can say, a reformed way of the upper or the more detailed way. As I said earlier, we read this kind of sequence from top to bottom like this, like we are going as a staircase, okay, and up to the response, and that's it. When we get our response, that means the procedure is ended or terminated or done, achieved. Okay, we may think about different types of sequence diagrams, and it depends on your scenario. It can be extremely detailed and you can say rigorous, and it's not easy for you to visualize it. However, look, I will not explain this one in details because it's very similar to what we explained earlier here, but look at this. Let's say we think about data transfer. Again, a medical receptionist and the PRS, the patient record system. Now, in the simplest form, the medical receptionist requests a login or tries to log in. Once the he or she is authorized to log in, then we can start or initiate the update or the view or the transfer of data, and then we can start the procedure. So what we explained earlier, okay? We may have, well, maybe update of data, maybe update of summary, whatever the scenario that we are going to have. And usually what we do, we don't have to represent the whole authorization as one column like this. It's just it has its own short lifetime based on the scenario. Once we get the authorization, then that's it, that's done. We are authorized to access and change information, update information, or whatever. So we can have these sequence of scenarios of update or change or add or provide a summary or whatever. Once it is done, it has to be marked by logout, and that will terminate the whole process, and then we will have our sequence diagram terminated. The idea here, you may say, or you may think, how do I know? How can I represent such a complicated system this way? Well, you are not the one who designed this meant care. So it's not exactly easy for you to describe this kind of interaction. But if you are designing a software yourself, if you are implementing the software yourself, if you are the one who is willing to create the model of the software itself, then you will know for sure what kind of interactions in details any action taken by an actor will do. So the sequence of the activities that will happen when an action is taken by an actor, you will be aware of. And that is how you design your own system based on sequence diagram or use case diagram. Then sequence diagram in details with no problem. Why? Because you are aware of what the system actually takes in terms of actions to produce whatever required from the actor. So that is exactly how we can go through it. After some time of your experience in software development, these things will be extremely easy to you, will be familiar, like things you pass through your life almost every day. So it will not be something difficult. What's authorization? Why it is like dotted line? Why this one is solid line? So in brief, this dotted line is exactly like the response from the instance of the object back again to where it is requested. As you see, these are the responses. So for example here, when we request the update of the PRS, there is certain request from one instance or some instance, and there is a message for granting the permission, or sometimes a message for telling that the update is done. Okay, so these things are usually quite often. If like we are requesting authorization, we get the authorization. If we are updating, then we get some feedback about the update, that it is done, and we tell the whatever the instance requesting this change, that it is okay, it's done, so terminate the procedure. And that is how we usually model the sequence diagram. I have already delayed while explaining this session. This is the end of the session. I hope you guys will enjoy and benefit from it. We have another session for this chapter. I'll try to record it tomorrow. Until I provide this second session, have a good time. Goodbye.